Now we're going to state an extremely important theorem in real analysis. I'm going to state the theorem and then at least do a sketch of the proof. It's called the Bolzano-Weierstrass theorem, and it's very simply stated. Every bounded infinite set has an accumulation point. Every bounded infinite set has an accumulation point. So let's take a look at the proof sketch. And the details I leave out are in your textbook, and I advise you to take a look at those. Well, the proof starts off this way. Let S be a subset of the reals that is bounded and infinite. And we're going to prove that that set S has an accumulation point. Well, for starters, since it is bounded, it has an upper bound and a lower bound, we're simply going to say let A and B be exactly that. A and B are real numbers, A is less than B, be such that the set S is entirely contained in the closed interval A to B. Again, A could be any lower bound for the set, B could be any upper bound for the set. And before I continue with the proof, let me draw a picture of what we're going to do. Okay, let's say this is our real line and our two numbers A and B, and the set S is completely contained in here. Well, that set has an infinite number of elements. I'm going to cut it in half. Hopefully that looks pretty close to the center. It's not great. I'll move it over just a little bit. I think that might be better, but just pretend like this is the middle, the midpoint. Since the interval AB has an infinite number of elements of the set S, so does this, or this. Either this half does or this half does. Think about why, by contradiction. If they both have a finite number of elements, then there's only a finite number of elements from A to B, and that's a contradiction. It's possible that both of them have an infinite number of elements, but at least one of them does. So I'm going to arbitrarily choose one. Let's say the one on the right. Let's say that this has infinitely many elements. And I'm going to call this A1 because I think that's what I call it in the proof. Well, cut it in half. Since A1 to B has infinitely many elements, so does either the left half or the right half. This time, let's say it's the left half. Let's say it's here. This has infinitely many elements. Infinite number of elements. And I could call that A2, B2. Take half of that. That one has an infinite number of elements. And we're going to proceed in an inductive fashion to help us in this proof. So that's how we're going to do it. Okay, so we've got this interval from A to B. I now need the midpoint. I'm going to say let A1 be the midpoint of AB. And what's that? It's the average value, B plus A over 2. A plus B over 2. That's the midpoint. Okay, so either, in that case, either the left half, which is alpha to A1, or the right half, which is A1 to B, has infinitely many elements of S. And whichever one it is, I'm going to rename it. I'm going to say call it A1, B1. So I don't know whether A1, B1 is the left half of AB or the right half of AB, and it doesn't matter. All right, let's let A2 equal the midpoint of that interval, A1, B1. A1 plus B1 all over 2. So either A1, A2, or A2B, sorry, that'd be A2B1. That's one of the halves, the left half or the right half of this has infinitely many elements of the set S. Let's call whichever half it is A2B2. All right, so from this point, I'm just going to say continuing in this manner, or this fashion, we define intervals a(n), bn for all natural numbers n. We defined an infinite number of intervals, and such that the following all hold true. I'm going to write down 3 or 4 things here. Number 1, little I. What is the width of each interval? The width of each interval is bn minus an. That's the width of the nth interval, and that's equal to beta minus alpha over 2 to the n. Let's make sure that works. Well, let's start at the very first interval. Well, the first interval was AB. If you want to think of that as A0, B0, this will still work. B minus A, okay, let's see. What I did wrong was I should have called this alpha and beta, but it's okay. I can just use this to be A minus B minus A. So the whole interval to begin with is length B minus A. B minus A divided by 2 to the 0, if we consider that our 0th term, is just B minus A. Then the second one, A1, B1, is half of this. It's either the left half or the right half of that interval, and that should be, the width of it should be B minus A divided by 2, which would be B minus A over 2 to the 1. And the next one would be B minus A over 2 to the 2 squared, and over 2 to the 3rd, and so on. So part 2 about our intervals AN, BN, each one of the intervals AN, BN contains infinitely many points of the set S. Point number 3 of the intervals is that AN, BN is a subset of the previous one, AN minus 1, comma, BN minus 1. That's a subset of AN minus 2, BN minus 2, that interval, and it goes on and on until we get up to A1, B1, and then finally AB. That's true for all values of n as well. If you start at 100, A100, B100 is an interval that is exactly half of this interval, and it's contained inside it. You remember, it would either be the left half or the right half of this interval. This interval is either the left half or the right half of this interval. All the way up to here, A1, B1 was either the left half or the right half of the original interval, AB. So I'm going to try to tie this up by saying that it turns out that T which is the supremum of the set A1, A2, ... is the accumulation point of the set S. It's the one that we have constructed here. It might be that there are other accumulation points, but this is certainly one of them. So what are we doing here? We're taking the supremum of this sequence of numbers. What do we know about those sequence of numbers? If you think about back to those intervals, let's say this is A1, B1, and let's say then we did, this became A2, B2, and then let's say the right half became A3, B3, and so on, A4, B4. Notice what's happening. A1 is an increasing sequence of numbers. B is a decreasing sequence of numbers. And if you want to think of the limit as n goes to infinity, they're going to meet each other somewhere in the middle. And it turns out that this T, I could have done this. Or T is the infimum of the B's. Infimum, the greatest lower bound of the B's. That's unnecessary, but I could have chosen this instead of that to be the accumulation point. So I will write that more details are found in the text. But one more sentence, all that's left to show, it remains only to show that each one of the neighborhoods, that every neighborhood of T contains infinitely many points of S. And therefore, that point, T, is an accumulation point of the set S.